Hello, everyone. Good morning, all of you.
Morning.
This screen is taking next slide also onto this, but so the space occupied by this will be reduced. So can we make it on the full screen?
Go to display settings.
Mm,
No.
okay.
1 second, click on slideshow.
Slideshow. Okay.
Yeah.
So here,
No. Just go to slideshow, sir, again.
actually, I click it here.
Yeah. Click here, sir. There is the display settings over top.
Yeah.
Click there.
Screen.
Yeah, click on that. Swap presenter view and slideshow.
Okay. So then it will be nice because that also, if you occupy screen, the slide will be size will be reduced. Okay. Good morning, all of you. So today's quote is "Don't cry because it's over, but smile because it happened." Okay. So anything, whatever happened, be happy about whatever is happened. Don't cry because it's over or it's going like this. And today is the birthday of Gillette. I think you are familiar with this name. Who is Gillette? Whoever now
Shame.
all having beards and
Yes,
using
sir.
glasses
Shame.
and all, right? So people of your age will know about this name actually, right? So he was an American inventor and manufacturer who invented and manufactured the safety razor with disposable blades. After persistent efforts to invent something that everyone would use, by 1895, produced a crude version of a disposable razor blade. It took another 6 years to refine his invention. On 15 November 1904, he was issued US patent for his idea and founded the Gillette Safety Razor Company in Boston to make his razor and blades. In 1903, he sold 168 blades. So this is one of the main thing actually, that perseverance, the confidence, and we should not lose patience, that hope should be there like that. So in 1 year, in 1903, he sold 168 blades. But in the following year, he sold 90,000 razors and over 12 million blades. Then he became a millionaire. A utopian, he wrote 4 books translating his business experience into social theories, culminating with the People's Corporation. Okay, so we'll go to CFD. And today we are going to discuss about numerical methods. It's like a revision of what you have studied in your last semester, numerical and statistical methods, or this semester.
Last semester.
Last semester. So because you are a bit fresh, you can just have a revision, because as I told, it is application of numerical methods to solve the partial differential equations.
Not last semester. It was in the fourth semester.
Fourth semester, yeah, 2, yeah. So so numerical methods you have to be a little bit familiar with. So so we will have a revision about it. Actually, we are applying numerical methods to partial differential equations, but that portion will not be covered in that. So it will be up to ODE, ordinary differential equations. Okay, we'll do revision up to that, and partial differential equations we will do in our CFD course. And just we'll just review what we have done in the last class. So we have seen what are the course outcomes of CFD subject, what is expected after doing the CFD, and we have described various chapters of CFD subject, and some results of CFD in various fields are shown, the post-processing results. And then we have discussed about software development process. So if you want to develop a software for a particular problem, so what are the various things like programming style, okay, and algorithm design and flow charting, pseudocode, structured programming, what are the rules for structured programming, and after that, how to debug it, what are the various types of errors we come across, and testing, what are the stages of testing, right? The modular test, the complete test, and the alpha test, beta testing, like that, and documentation, internal and external documentation, what actually it deals with, and then storage and maintenance. Okay, these are the things we have discussed in the last class. And today we go for numerical methods. This is again from the same book. So we first chapter a little bit, and then every chapter has actually it is divided into part 1, part 2, part 3, part 4, like that. Every part has an epilogue. Okay. In that epilogue, there are subtitles like trade-offs and the important formulae and relations, like that. So we concentrate only on that. That the essence of each part we will discuss, because already, as I told, it's like a revision, right? We discuss with that. Okay, that book is very good for revision. And actually, that book is meant for applications of numerical methods in engineering. Okay, in various engineering fields, he has given beautiful problems in every chapter, like from electrical engineering, from mechanical engineering, from civil engineering. What are the types of problems we come across, and how these numerical methods can be used in those problems? Real practical problems, live problems, you can see in that book. It's a fantastic book. I don't know whether we have come across during that semester, but because mathematicians, when they teach, they take different books. But when yeah, technical people or engineers teach, they take the books which are useful for the engineers. Okay. We see just lightly discuss what is the approximation and what is round of error, what is accuracy and precision, what is significant figures and chopping, and the types of problems in numerical methods. And then these are the things which you have studied: roots of equation you have studied, and solution of simultaneous algebraic equations you have studied, and methods of curve fitting you have studied, numerical integration, and solution of ODEs. But the solution of PDEs you have not studied. Okay, these things we'll discuss in brief. Trade-offs, as I told, because there are various methods are there. Whenever there are options are there, okay, some more than one method, 2 methods, 3 methods, 4 methods, 5 methods, like that are there, we have to understand the trade-offs. What are the advantages and disadvantages? What are the places where we can apply them based on understanding the comparison? Okay. Okay, so approximations and round-off errors. As I told, the numerical method itself is an approximation. Okay, the solutions are approximate solutions. So there will be always round-off errors. And this round-off error is very, very important in computational fluid dynamics. So when you are calculating suppose a variable at a particular node, so we have to round it off. Because of the computer, I have to round it off. There is no other way, because there will be number of digits it can handle based on the length of the number. Like if it is integer, there will be 4 bytes. If it is a real number with single precision, so many bytes, and like that, we have a limitation over that based on the computer. So only up to certain digits it can take, and then it has to either chop or round off. Okay. So there will be round-off error. And what is the effect of round-off error? If I have some round-off error at a particular node, because the values at other nodes are calculated using this particular node where it is rounded off. So what is the effect of this error on the subsequent nodes? Whether the round-off error, the effect of round-off error increases the overall error there, or so how this error propagate. So those things we will discuss when we discuss about error analysis. Okay, so that is about error. There are 2 types of errors when we come across. Like so there are 2 types of errors we will get. One is truncation error, and another is round-off error. So truncation error comes from the formulation. So based on our formulation, how much truncation error means, actually we are going to use Taylor series expansions. So in the Taylor series expansions, we consider only up to some, because it's infinite series, right? We consider only up to certain terms, and then we neglect the higher order terms. So that is called as truncation. Okay, truncation error is in the formulation. So whether you want to have second order accuracy, third order accuracy, or fourth order accuracy, So based on that, I consider the number of terms in the Taylor series. And round of error, it is inherent in with the system or computer. Okay, so this is the round of error that we get from the computer, and this round of error, if you want to reduce, sometimes what we do is we will have what is called a single precision, double precision, and quadruple precision. Like that we have. Like if you remember, we will have float, and what is the other one? If you want more precision,
Doubles.
double, and still higher. Anybody knows?
Long double kind of things.
Long float.
Long float.
Yeah, long float, long double, like that. So we can increase the number of digits that we consider, and but it depends on how much accuracy you want. Sometimes it increases the load on the computer if you take more number of digits. Okay, so we have to have again trade-off between them. Okay, then we discuss about what is accuracy, precision, inaccuracy, and imprecision. And precision is what is called as reducibility, and inaccuracy is called as bias, and imprecision is called as uncertainty. Okay, so here accuracy means the difference between the measured value and the true value. You might have studied in your experimental methods, similar things, right? And precision is how much you can reproduce. It depends on the subsequent value, measured values. Okay, it doesn't depend on the true value. So what is the value I measure now, and then what is the value I'm going to measure? So the difference between that is precision. It is nowhere dependent on the true value. It is only within the measured values how much variation is there. Okay, so inaccuracy is a deviation from the actual value, and imprecision is the deviation among the measured values. Okay, so that is imprecision also is called as uncertainty. Okay, if you just look at this, okay, so when I am shooting it, suppose a target, a bullseye. So here, this is what type of this is?
Inaccurate, imprecise.
Yeah, imprecise and inaccuracy. It is actually increasing accuracy, and this is increasing precision. So here minimum accuracy and minimum precision is there. So as you go this side, accuracy increase means all of them come towards the center. Okay, so if you see, it is around the accuracy. Highest accuracy means the average of all the values will be accuracy, but nothing, each measured value is different completely. Okay, but if you see the average, it is around the accuracy, around the true value. Okay, so this is highly accurate. So if you see this, you can see that highly precise it is. It is highly precise, but it is away from the true value. So it is accuracy is less, but precision is high. But if you see this, I have more precision and more accuracy. It is all near to the true value, and also all values are near to each other. Okay, so this is a difference between accuracy and precision. And the significant figures, how many significant figures we are interested in. Okay, so here, suppose this is the value. If I write it as 5.38 into 10 power 4, this is 3 significant figures. And if I put 5.380 into 10 power 4, I have 4 significant figures. And this is 5 significant figures. But when you come to the floating point values, zeros are sometimes used to locate the decimal point and not significant figures. Suppose 0.1753 is there. If I put 0.001753, 0.001753, whatever you, all these are having only 4 significant figures. Okay, so here these zeros will consider come into the significant figure, but these zeros will not come into the significant figures. So this difference we have to understand. And the error. So there are various values. True value is approximation plus error, or error is equal to true value minus approximation. So what is true relative error? True fractional relative error. True error by true value. Error percentage if I want, true error by true value into 100%. Okay, this is about this. But if I know the true value, I can find out the error. But if I don't know, because when I'm doing the calculations, I don't know the true value. I'm trying to find out it. So how to calculate the error? So there is approximate error and approximation. So for numerical methods, the true value will be known only when we deal with the functions that can be solved analytically. If I have exact solution, then only I will have true value. In real world application, we usually not know the answer a priori. So then approximate error by approximation. So first approximation I will have. So the next approximation or updation I will have. So the difference between these two is called the approximate error, or current approximation minus previous approximation by current approximation. So this is relative error into 100. It is percentage error. So in iterative approach, whatever we are going to do in numerical methods, so we have to use this particular one. Okay. And we have to use absolute value, and computations are repeated until stopping criteria is satisfied. So that is very important when I are doing the iteration process. So I have to give some stopping criteria, because otherwise it will be an infinite loop. So I have to calculate the error after each iteration, and I have to check whether it is less than some specified error. So that specified error I have to give at the beginning. Okay, whether 0.001 or 0.0001, like that, how many digits you want the accuracy. Okay, so this is the approximate error, but less than if epsilon s. This is pre-specified percent tolerance based on the knowledge of your solution. Okay, so I have to keep them some specific criterion. So and here modulus is important, because if it is 0.001, and if I have an error calculated is -5, it will come less than that if I don't take absolute. Okay, so I have to give the absolute value. And sometimes you will be given, you have to get the solution for 3 significant figures or 4 significant figures. Then what is epsilon s? So I have to use this formula, 0.5 into 10 power 2 minus 10 percent. If it is from 5 significant figures, it will be 10 power minus 3, 0.5 into 10 power minus 3. So that should be epsilon s, or specified error. And round off error, that you know, right? If you want to round off at a particular point, so the next digit I have to check whether that is less than 5 or greater than or equal to 5. If it is less than 5, it will be left as it is. If it is greater than or equal to 5, I have to add 1 to the digit at which we are cutting. Okay, this is the binary numbers and decimal numbers, how we calculate 9 into 10 power 0, 0 into 10 power 1, like that. And in the same way for decimal, binary, 2 power 0, 1, 2, 3, 4, like that, we will calculate what is the binary number. Okay, one interesting puzzle I will ask. Suppose you are given 1,000 rupees. Okay, carefully listen. You are given 1,000 rupees, and you are given 10 boxes. You have to distribute that 1,000 rupees into those 10 boxes in such a way that whatever be the amount I ask, whether it is 1 rupee or 156 rupees or 935 rupees, whatever I ask, you should be in a position to give me without opening the boxes. Okay, some combination of boxes should give me the required amount. Am I clear about the problem? Are you there?
Yes, sir. Yes, sir.
Yeah.
Problem is clear.
You are given 1,000 rupees and 10 boxes. You have to distribute the 1,000 rupees in those 10 boxes in such a way that from 1 rupee to 1,000 rupees, whatever amount I ask, you should be in a position to give me without opening the boxes, using a combination of the sum of number of boxes. So what is the way I have to distribute those that money into those boxes? Okay, keep that in your mind. Okay, we will discuss at the end of the class. Okay, in the binary number, suppose it is 16 digits. So the first digit represents the sign. So how to know whether it is positive or negative? Anybody knows?
Sir, 1 is positive, 0 is negative.
What is that?
Sir, 1 is positive and maybe 0 is negative.
Yeah, it is 1 or 0. So how to know whether it is positive or negative, the other one?
Sir, if 1 is there, then maybe the number is positive.
Very good, right. If it is 0, it is positive. If it is 1, this is negative. So I have to use only these other digits and get the number and put minus sign if it is 1. Okay, so that is the way we put that. And suppose 156.78 is there, it is 0.1578 into 10 power 8 on a floating point base 10 system. So suppose 1 by 34 is there, if it is this, suppose only 4 decimal places are to be stored, so it is 0.0294 into 10 power 0. Okay, but sometimes we'll be asked to normalize it. So normalizing means, suppose this is normalized, okay, so then it will be written 0.1, 0 point, all the digits should be on the right side, and whatever 10 power I have to give like this. That is exponential notation or scientific notation. When you give, I have to give it 0.15678 E3, okay, like that. So in the same way, 0.0294 into 10 power 0 is to be written as 0.294 into 10 power 1. Okay, or 10 power minus 1, sorry. Okay, so that is the way we have to give the scientific notation. And floating point representation allows both fractions and very large numbers to be expressed on the computer. However, floating point numbers take up more room. It takes more space compared to integers. And it takes longer to process than integer numbers. Floating point calculations will take more time. And round-off errors are introduced because Mantissa holds only a finite number of significant figures. Okay, so that is about the floating point calculations. And chopping. Chopping means truncation. And up to certain digits, there are two types, okay, chopping and truncation. Chopping and rounding off. Chopping means just cut it off at that, the remaining digits will be removed. And if it is rounded, it sees where it is cut off, and based on that, the number before that should be either the same number or one increased. Okay, that is what is called as rounding down or rounding up. But chopping, it doesn't matter. Whatever be the digit that is cut there, so it will not matter. Okay, but so because some machines will chop it, some machines round off. And some machines use chopping because rounding adds to the computational overhead. So if I want to round off, every time it is rounding off, it has to see what is the digit it is cutting, and then it has to round up or round down. So every time it has to, that increases the CPU time or overhead on the computer. But since number of significant figures is large enough, resulting chopping error is negligible. So if you see here, and if I chop here at 2, okay, so here the error is 0.000065. But if it is rounded off, so this 2 will be here made into 3 because here 6 is cut. So if it is put 3, the error is like this 35. Okay, so the round off error is more in chopping and less in rounding, but you can see that the amount actually, because it is so after so many decimal places, for many calculations it may be negligible. Based on that, how much important is the contribution of that? Okay, so whether it is drastically changes your final solution, then you have to be careful. If it doesn't matter, you can just better chop it off so that the overhead on the computer can be reduced. Okay, so types of problems in numerical methods you have studied in your syllabus, like roots of equations, systems of linear algebraic equations, optimization. Optimization also, I think you didn't study. Okay, that anyhow is not needed. I have given this because it is covered in the chapter. So, but you need not worry about optimization. And curve fitting, and in curve fitting we have regression and interpolation. And the numerical integration and ordinary differential equations. And as I told, partial differential equations also, there is one chapter there, but you just ignore that. Okay, then, so what do you mean by roots of equation? So there will be a fx equal to 0 when function is given, and the root of the, because if you draw the graph, there is one particular value of x which gives the function value to be 0, and you can draw it. If you draw graphically, you can find out what is the root. But numerically, we have to see what are the different methods to find out this particular root. Similarly, linear algebraic equations, if I have two equations, graphically also I can solve this by drawing the two lines, right? These are the two lines, and the intersecting point gives me the solution. And using numerical methods, we have to see what are the various values. Like optimization, if you have a function x, and if you want to find out what is the minimum function or what is the maximum value of the function, if you can draw the graph, you can find out, or you have to use the methods. Then curve fitting, there are two types, as I told, regression and interpolation. Can you tell me what is the difference between regression and interpolation?
Regression is fitting the curves and the known values. Interpolation is will extend the graph with the known values.
Still better answer. Anybody else? By seeing the graph itself, you can make it out.
Sir, in interpolation, it passes through the every point, sir. But in regression,
It is a
most
best
likely curve will be formed.
regression is nothing but a best fit. Okay, it need not go through any value. It may go through some values, but it will give a best fit. Okay, so that is regression. And interpolation, as he was telling, it goes through all the data points. Okay, so that is the difference. So if you are normally calculating using analytical method, so interpolation works well. It goes through all the points. But if you are doing an experiment, you are going to get some random points. So you will not get exact points, right? Because there will be experimental errors and all. It's always better to draw a best fit or regression. Okay. So that's why many times we say when you are, because you are not doing experiments in thermal lab and all. So when you do thermal lab and you get the graph, okay, you might have drawn it, and I don't know how you have drawn it. And those lines, though you know that it has to come something like this, or it has to come a straight line, many times people do what they do is they draw a graph going through all the points, and a horrible line will come. So you will not know exactly how they are related. So it need not be like that. You have to always draw a best fit only. So that is important. Okay, integration is nothing but finding out the area under the curve. And anybody remember some of the methods of numerical integration? Anybody remember some of the methods of numerical integration?
Sir, what do you mean by methods, sir? I don't understand your questions.
You didn't understand.
So by part method for integration.
Trapezoidal method.
Yeah,
Simpson method, sir.
trapezoidal method, Simpson's 1/3 rule, Simpson's 3/8 rule, like that, isn't it? And similarly, suppose roots of equation, if you say, what are the methods do you remember?
Newton-Raphson method.
Yeah, Newton-Raphson method, very good. Any other methods? Bisection method.
False position method.
Regular falsy or false position method, Newton-Raphson method, point iteration method. These are various methods for finding the roots of equation. And finding out the solution for linear algebra, simultaneous linear algebraic equations. Anybody remember some names?
Gauss-Seidel method.
Gauss-Seidel method, very good. So
Jacobi iteration.
Jacobi iteration, right.
Cramer's
rule. Cramer's rule, actually, it is not a numerical method. This is actually direct method. Okay, so, but that is also a method. And Gauss elimination, right? Gauss elimination method, Jacobi iteration method, Gauss-Seidel iteration method, and there is LU decomposition method, which you may not come across LU decomposition. And okay, these are the methods. So we will just briefly go through them. Okay, it is just a problem solving process. You give problem definition and find out the mathematical model using the theory and data, and various problem solving tools we have to use, either computers, statistics, numerical methods, graphics, etc., and find out numerical or graphical results. Then using interfaces like scheduling, optimization, communication, public interaction, etc. So you have to implement it. Okay, it is just a problem solving process. Okay, and as I was telling, because there are various types of processes, we have seen bisection method, regular falsifier method, Newton-Raphson method, like that, and Gauss-Seidel, Gauss iteration, like that. We have various alternative methods. So we have to know the trade-offs. That is, advantages and disadvantages of each of the one, or relative merits and demerits we have to know. And so which is to be used? Okay, it depends on various characteristics like type, availability of the information, and precision of the method, cost of it, and speed of computer. It depends on all these things. And also program development cost, software cost, runtime cost, and what are the characteristics of numerical methods, like all these things given here. Number of initial guesses you have to make or starting points. So if you remember bisection method, I have to have 2 initial guesses. If I have Newton-Raphson method, I have to have 1 initial guess. So initial guess itself is difficult, because unless you know the physics of the problem and you know the real world problem, you don't know exactly what is the guess I have to make. Okay, some idea I should have. I ask you to, by showing some item, I ask you what could be the cost of it. You should have some idea, right? Otherwise, just you have to tell some number at which other people may laugh. It may be completely impractical. So one initial guess itself is difficult. Sometimes more than one initial guess, if you have to do, then it will be difficult for you. So it depends on the initial guesses or starting points and rate of convergence. So how many iterations it takes. So that also is important, because computer time, right? So how much time you will wait, how much iterations will take, and what is the overhead on the computer. And so if you remember in the roots of equation, there is one method which have faster convergence. Which method? That is Newton-Raphson method. Okay, Newton-Raphson method has quadratic convergence. We call it a second order convergence. Others are having linear convergence, and Newton-Raphson method has quadratic convergence. And stability, okay, how stable it is. As I told, if it oscillates and goes on for a long time, then it is less stable. And then how accurate it is, how precise it is for various, again, if you repeat it, whether it gives the same solution or not, whether it's the accurate solution or not. Breadth of application, that is the range of application, how many types of problems you can solve, and any special requirements are there. So what is the programming effort required? These are the various things based on which you have to decide which method is suitable for you. Okay, this already we have done this error definition and all. This is not necessary. Okay, methods to find out the root of a nonlinear equation. Sometimes we call it as transcendental equation, whatever we have discussed. So an equation having trigonometric quantities like sine, cos, and all, logarithms, natural logarithm, or based on logarithm, or if you have exponential functions. So anything can be there. And that is called as nonlinear equation. Linear equations, you know, right? Okay, like a naught x power n plus b1 x power a1 x power n minus 1 a plus a2 x power n minus 2, like that. If you have a polynomial equation, that is a linear, it's not linear equation, it's a polynomial equation. A nonlinear equation, it can be anything. And sometimes it is called as transcendental equation. So it can have trigonometric functions and logarithmic functions. and exponential functions and a combination. Anything like suppose 5e power x plus 6 sin x plus 8 log x equal to 0, something like that. So a function of this sort, we call it, and it can have even an x power like that. Okay, so the combination of all of these things, these are called as transcendental equations. So it should be these types of equations are to be solved. So these are the methods: bisection method, false position method, Newton-Raphson method, and secant method. Okay, so these are the main methods we come across. So bisection method, it requires two values, if you remember. So how to check the two values, or how to choose the two values? Can anybody say?
We'll put some random values and we'll check for change in sign
Yeah.
between
So
the
one value should give me a positive f of x, and one value should give me a negative value of f of x. So that f of x equal to 0 will be between these two values. Okay, so I have to give the two initial guesses in such a way that the function becomes positive and negative. And then I have to find out what is the actual root. So what we do for that? The next approximation, I have to take the average of these two, bisection. Okay, so I have to bisect it, and I have to see what is the value. If it is a negative value, previous one which gives positive value I have to take, so that my range of range gets reduced. Initially both root approximations are away from each other, then it will be first half or second half in which the root will be there. So in that way I have to move towards the root. So this is like this. Okay, so I have to take one value on this side, one value. So xu is the upper one and xl is the lower one. So the next iteration will be xl plus xu by 2. So then I have to check it whether the function value at this point and the other one xl, because the product of the function values at two ends must be negative. So based on that, I have to check whether I have to take the left side portion or right side portion. So in the left, if I take the right side portion again, the next approximation should be half of that right side portion. So I will have quarter portion. In that way, I have to reduce the range. I go on reducing it till you get to the root. Okay, so that is the way I have to use the bisection method. And false position method, here also, how many guesses I make? Two guesses only. One on the negative side and one on the positive side. Here, like xl, this function value is negative, and the xu, it is function value is positive. So the next approximation will be, if you draw a line, wherever it cuts the x-axis, that is taken as the next approximation. So you can see that this is the actual root, and the approximation initially these are the two guesses are made, and the next one it is coming to this point. Okay, so it is coming very near to the root. So what will be the next approximation? So I have to see what is the fx value here. Is the fx value negative or positive here?
negative.
Negative. So I have to eliminate this xl here and shift xl to this point. Okay, and then this f point and this f point are to be joined, and then it moves very much towards the root. Okay, in that way I have to move towards the root. And Newton-Raphson method, how we do it? There is only one guess. Okay, so this guess, suppose it is this guess, draw a tangent wherever it cuts the x-axis, so that will be taken as the next approximation. So you can see that it is coming to the root very near to this. But only one thing is, whenever I have a method with two initial guesses, that is called as bracketing method. Okay, this is important. So we have bracketing methods, and other is what is it called as? Okay, I will tell you what it is. Bracketing methods means it will have two initial guesses, one on either side. Okay, one on the negative side, another on the positive side. So it definitely converges. There is no question of diverging because it's always one on both sides I am making, and I am reducing the gap between those two. So, but the other method with only one guess, right? It may or may not converge. Based on the initial guess, okay, sometimes it may come, the new approximation may move towards the root, or it may go away from the root. But if at all, if it goes towards the root, it goes very fast, like Newton-Raphson method. Okay, but it is not definite that it may converge. There are some tests of initial guess, how to make the initial guess. Okay, now we are not going to discuss about it. Okay, so like this. And secant method, this is an exception. Here I make two guesses, but it will not come into bracketing method. Right? But so initially when I make two guesses, I just don't care whether it is on either side. Okay, it can be on the same side. But the method of solving is like regular falsi only. That is, I suppose these are the two guesses. So in regular falsi, what I am doing, join these two and extend it. Wherever it cuts the x-axis, that is taken as the next approximation. But at that time, I have taken one on this side, one on that side, and I have cut. But here, both can be on the same side. Okay, so I don't care whether one is giving negative value, one is positive value. Just I take two random values and start it. It may converge or it may not converge because it is not bracketing the root. Regular falsi, it has two initial guesses, but it is not definite that it will converge. So false position method sometimes converge very slow. Okay, suppose this is the initial values, these two. So if I draw it, this is the next updation. Okay, so it is giving negative value. So this point and this point is to be joined, and then the new value will come here, and this function value here, and again you join. Like that, it goes very slow towards this. Okay, sometimes it happens, but always it may not happen. It depends on the type of function. And there are 4 cases where Newton-Raphson method shows poor convergence. Okay, suppose this is the function. As I told, it gives, if it converges, quadratic convergence, it goes very fast. But it depends on the initial guess. Sometimes initial guess may make the solution like this. Suppose this is the first guess. Okay, this is the first guess. And if you draw the tangent, it is coming here. This is the root. Okay, so this new approximation is coming here, and this is the function value. Draw tangent here, it is coming here, next approximation. And if you find the function value here, and again if you draw a tangent, it is going very far. That is what is called as diverging. It is going away from the root. So this is one case. And another case, it may go like this. Okay, it goes like this, tangent here, tangent here, tangent here, like this, and finally it is getting diverged. So whenever I have a function of this sort, it may happen in that way. And suppose here if you take, right, so it is going away like that. Okay, initially this is this, it is going away from here, and it is going away from here. Actually there are multiple roots. These are multiple roots, but it is going not picking any one of the root even nearby. And so sometimes it completely goes away, the tangent goes away, and complete divergence will be there. So there are various, based on the initial guess, right? You may have either faster and quadratic convergence and many times for different types of guesses based on the function and initial guess. So it may completely diverge. And here, this is the trade-off. Okay. So direct method, graphical method, and direct means analytical method. Graphical means visual method. Okay. If you draw a graph and find out the root. And bisection, false position, modified false position, fixed point iteration. Okay. Fixed point iteration. Anybody knows what is that? Have you heard about it?
No, sir.
Suppose f of x equal to 0, right? And I have to find out x which satisfies that. So it is something like this. Oh, sorry, it's not like that. Xn plus 1. The new approximation must be, I have to write this as x is equal to f of x. I have to write this function f of x equal to 0 as x equal to fx. Then I have to write this as fxn plus 1 is equal to f of x. Okay, it is like this I have to write. Suppose just for example, I will write you x square plus sin x, okay, 2 sin x plus 5e power x equal to 0, something like this. And I have to write this in this form. I can write in various methods. Like suppose I can write this as x square equal to minus 2 sin x minus 5e power x and x equal to root of this. Like this I can write. Or I can write this as 2 sin x is equal to minus x square minus 5e power x, and x is equal to, okay, by 2 I will write sine inverse of minus x square minus 5e power x by 2. So like this I can write. This is another way, and this is one way. Or I can write e power x equal to minus x square minus 2 sin x by 5, or x is equal to log of this, okay? Something like this. Okay, natural log of that. So in this way, I have to write x equal to f of x form, okay, this form, and then give some approximate value to x. Okay, so x1 or x0, I assume it to be 0, and substitute here in one of the function. You take one of the function, not different, only one. So if I take this particular function, substitute x equal to 0 here, and find out the new value of x. So x1 I calculate. And using that x1 substitute here in this expression and update x2. So you calculate the new value of x and find out the difference between these two. If it is very near, it is converged. Otherwise, using x2, you find out x3. Am I clear about this method?
Yes, sir.
Yes, sir.
So, yeah, this is called as fixed point iteration method. This is the easier one. You need not make any guess also. So fixed point iteration method, Newton-Raphson method, modified Newton-Raphson. Okay. Previously, I was telling bracketing method one. Another is open method. Okay. So if you see what are the types, the bisection, false position, modified false position, these are bracketing methods. And fixed point iteration, Newton-Raphson. In that, okay. So guesses, these bracketing methods needs 2 initial guesses. Secant method also need 2 initial guesses. The others only 1 initial guess. But if you see, this secant method, though there are two, it is possibly divergent. So all these single assumption, guess, and secant method may diverge, but this converges always. Okay, and so which is medium, which is low, all these given, right? You can have, this is the trade-offs comparison. And application, it is something like suppose in an example taken from the Chopra only. So I have the equation of state for a real gas, P plus A by V square into V minus B equal to RT. And I have values of A, B, because it depends on the gas, right? For carbon dioxide and oxygen, the values are given. And so R bar here per mole in the mole equation, this is R bar, universal gas constant, we know it. And so different values of pressures and temperatures are given, and you have to find out the volumes. So because we know that so P plus A by V square into V minus B is equal to RT V1. Okay, so I know P and T. Okay, A and B are constants. So for a given P and T, I have to calculate V. So how to calculate the V? I have to solve this. Okay, so what I do is I will write this as P plus A by V square into V minus B minus RT equal to 0. So once I get f of x equal to 0, like f of v equal to 0, I can use any method. It can be bisection, regular falsy, or anything. Am I clear?
Yes, sir.
So that is just one of the application. So another application is given. Suppose RLC circuit is there, and we know this. This is the equation, right, for RLC circuit, and this is the analytical solution. And so here, Q naught to calculate R for a given combination of capacitance and inductance. I have to calculate R. So Q also is given. So I have to find out what is R. So you can see that this is a complicated transcendental equation, and I can calculate R using one of those numerical methods. So I will write it as I'll take one side and equal to 0. So f of R, this is equal to 0. So this equation is to be solved to get R. Okay, this is the way we can have the practical places where I need numerical method to solve a transcendental equation. Okay, these are some examples. Okay, then methods of solving linear algebraic equations. In that, do you remember what we do? What is the method of Gauss elimination method? So you are given Ax equal to B. Okay.
Sir, you are lagging very much, sir. That's why we are not able to get you sometimes.
Okay, okay. So in Gauss elimination method, I am given A matrix and B matrix, and I have to get the X values. And so what we do in Gauss elimination?
Forward elimination and back substitution.
Yeah. Forward elimination, sorry. First step is to make upper triangular matrix. Make A an upper triangular matrix. Okay, by what is that, row operations. So row operations, you know, by making the row operations, I have to see that I will get something like A1. Okay, upper triangle. Like this. Okay, something like this. After some row operations, I may get in this particular form. So then A6 is equal to A6 into X3 is equal to C1. So X3 is equal to C1 by A6. I can find out. Then A4X2 plus A5X3 is equal to C2. So I know A4, I know A5, I know C2, and in this X3 is already calculated, so I have to use get calculate X2. So like that, I will come here. Knowing X3, I can calculate X2. Knowing X2 and X3, I can calculate X1. This is called as backward substitution. Okay, forward first we have to make it upper triangular matrix. Then using backward substitution, I can solve this right like this. This is called as Gauss elimination method. And there is another method called as LU decomposition. I will just brief it. I think you have not studied this. I'll just brief it. This is another important. Actually, this is widely used in finite element method. Have you heard about, have you anybody done FEM? Is there anybody? Okay, so any matrix, now I have AX equal to B. So any matrix can be written as a product of lower triangular and upper triangular matrix. Okay, hope everybody is listening me. Okay, any?
Yes.
Okay.
Yes,
Okay.
sir. Yes.
Okay. So here, how to any matrix can be written as a product of lower triangular and upper triangular matrix. But how to get it? So this is done like this. So I will have A1, A2, A3, B1, B2, B3. I am writing just three equations, but it is true for anything. I have to write this like this. The lower triangular matrix will be in this form. And upper triangular matrix U1, U2, U3. Like this. Okay, now I have to get this matrix and this matrix. How many unknowns are there?
Three, sir.
How many?
3.
No. I have 6 plus 3. Here 3 unknowns.
Yes, sir. Yes, 9.
Unknowns. So 9 unknowns are there. And how many equations I will get?
3.
3.
9 equations, sir.
9 equations I will get. So here, how do when you multiply, I will get 9 elements, right? So
Yes, sir.
this-
9 equations will be.
So 9 equations, 9 unknowns, and I can solve for these L1, L2, L3, and all these 6 unknowns. 9 unknowns I can solve. That is, I can get the L matrix and U matrix. Am I clear about it?
Yes, sir.
Yes, sir.
Yeah. Once I get it, so AX equal to B. So I will put here LU X equal to B, right? So I will write some UX equal to D. So I will get LD equal to B. And what is the finally I want? I want UX equal to D. And so here L matrix is known and B matrix is known. And can I find D matrix or not? So
Yes,
here,
Yes, sir.
Yes, sir.
1, 1, 1, L1, L2, L3, 0, 0, 0, D1, D2, D3 is equal to D1, D2, D3. I can directly get D1 equal to B1. And then L1 D1 plus D2 equal to B2, I will get D2. So this is what is called as forward substitution. I'm first get D1, using D1 you get D2, using D1, D2 you get D3. Okay, so you can solve D matrix. So once you solve D matrix, U is known and D is known, you have to solve for X. Right? So here U1, U2, U3, 0, U4, U5, 0, 0, U6, and X1, X2, X3 is equal to D1, D2, D3. So when you do like this, I have to solve for X. So X3, U6 is equal to D1. So I can find out X3. And then U4, X1 plus U5, X2 is equal to D2. So I can find out X2. Like that, backward substitution. First find out X3 and then X2 like that. Is it clear? In that way, I can solve for X. That is what is called as value decomposition. It is very, very famous and widely used in finite element method. And these are called direct methods. And actually matrix solvers or it is not okay. So we have direct methods and iterative methods. Okay, Gauss elimination, value decomposition. I am not doing any iterations, like just I will get the solution directly x1, x2, x3. I am not using that values again and again like that and updating and all. I am not doing that. Even Cramer's rule also direct method only, but this is analytical. Okay, which you know already. And iterative methods, we have what is called a Jacobi iteration and Gauss-Seidel iteration. Okay, we learn like this, but the Jacobi iteration we never use. It is updated version of Jacobi, Gauss-Seidel iteration. Anybody remember how to do the Gauss-Seidel iteration method? It is like suppose A11 x1 plus A12 x2 plus etc. A1 and xn is equal to B1, and A12 x2 plus A22 x1 x2 plus etc. A2n xn is equal to B2. Like this we will write. And from the first equation, I will write it as x1 is equal to B1 minus A12 x2 minus A13 x3 plus minus etc. minus A1n xn by A11. Right. And x2 from the second equation, I will get 1 by A22 minus B2 minus A12 x1 minus A23 x3 minus like that. In that way, I will get xn. All these equations I will get. So first equation, I will write it as x1 equal to, and next x2 equal to, like that. So this way we'll write, and then we have to initialize the, suppose x1, x2, x3, etc. I will give 0 initial values. And substitute those values here. I will get a new value for x1. And substitute all these things. That is, x1 becomes b1 by a11, first iteration. x2 becomes b2 by a22 in the first iteration. So I will get all new values for x1, x2, etc. And use those values and substitute them here and to update the values. Am I clear?
Yes.
So that is the way we will go. This is Jacobi iteration. That is using all the old values if I am calculating the new values. But in Gauss-Seidel, what I do is, so once I calculate x1, this new x1 I will keep here. So that in the next equation, I will use new x1 instead of using the old value, because already it is updated, right? New value is used. And when you calculate x3, we'll use new values of x1 and x2. So that is the way the number of iterations can be reduced in the Gauss-Seidel iteration method. Is that clear?
Yes, sir.
So this is the way, and now the potential problems and remedies it is given. Actually, if you remember, Gauss elimination and the direct methods, solute decomposition and Gauss-Seidel, they give large round of error. That is one of the main drawback in these direct methods. That is one of the limitation in finite element method also. Okay, and as the size of matrix increase, the round of error will increase very much. Okay, so because I am using one to calculate the others, the round of error goes on increasing as the number of nodes or values are increasing. Iterative method is not like that. I calculate something, I take the initial values, I update them, and using those updated values again, I am calculating these values, right? So updated values only I am using, and my total error is always gets reduced, though initially it is high. So that is the advantage with iteration method, which is used in CFD. And one of the requirement is for Gauss-Seidel iteration method, I should have what is called as diagonal dominance. Okay, diagonal dominance must be there. That is here 1 by A11 will be there, 1 by A22. These diagonal elements, it must be larger. Okay, this is what is called as that is what is called as diagonal dominance. There is what is called as Scarborough criterion. What it says is AII should be greater than or equal to sigma Aij I not equal to Z. Okay, so the sum of all the non-diagonal values, so the diagonal value should be more than sum of all the non-diagonal values. Okay, like this. This is what is called as diagonal dominance. Fortunately, in all our CFD schemes, automatically the diagonal dominance comes. That's why we don't have problem. We can comfortably, we can safely use Gauss-Seidel iteration method. Okay, so this is the method we use. Okay, this is about those things you go through, and okay, this is graphical rule, Cramer's rule, Gauss elimination, Gauss-Seidel, and these comments, comparison, all these things you go through them. And method of regression, okay, we have linear regression, polynomial regression, and multiple linear regression. And there are methods of interpolation. You have studied this, Newton's divided difference interpolation method and Lagrange interpolation method, like that. Okay, so I am not discussing all these methods. Okay, and cubic spline method also. I think in CAD you might have studied. Have you studied cubic spline?
Yes, sir.
So this also goes through all the points, and it approximates a cubic profile between every 2 points. Every 2 successive points. Okay, so here, because there are 4 unknowns in a cubic, so this point gives one value, this point gives one value, and end conditions, that is the slope continuity, that gives the other values, and you can find out A1, B1, C1, D1 for each cubic, and you can draw a cubic spline. So do you know what is cubic spline? Spline it is called as, why it is called? Actually, in the olden days, draftsman used to be there. Now everything you are doing on the AutoCAD and all. But if you want to draw a curve going through all the points, and you find it always difficult to draw an ellipse or parabola or hyperbola like that, and if you have those number of points are there, drawing a freehand curve going through that in a very smooth fashion is difficult. So the draftsman used to have a flexible scale. So this much of scale like thing, but it is flexible. You can bend it in any way, it stays in that position. Okay, so he can he takes that and keeps on all the points touching them, and then he draws the curve so that it goes very smooth curve going through all the points. So that is what is called as draftsman's spline. And because this is cubic, and it is called as cubic spline. And again, there are trade-offs, right? So again, you go through them. So problems, where do you do? Normally, when you do an experiment, so you are going to get the points and you can calculate the values, and you can you should be able to interpolate for any intermediate value. Okay, so if you want to have a curve of this sort, Q is equal to A naught D power A1 plus S power A2 into S power A2. And I want to find out, because it is a nonlinear curve, I have to fit a curve. Okay, so if it is of this type of equation, I have Q values, D values, and S values. And if you substitute them, I am going to get equations. And so the unknowns are A1, A2, A3. And A0, A1, A2, I have to find out them. If I take logarithm, so here the unknowns are log A0, A1, A2. Okay, so give the tabular values are there, this diameter, slope, and flow, Q, D, and S. You substitute them, you are going to get equations. And if you put them into equations and you can solve them, you can solve for A0, A1, A2. In that way, you can fit an equation for that. And then numerical integration, trapezoidal rule, and multiple application of trapezoidal rule and Simpson's 1/3 rule, and multiple application of Simpson's 1/3 rule, Simpson's 3/8 rule. All these things we have studied already. And so it is like this. Okay, so I fit a trapezium here. Okay, I take these endpoints, I fit a trapezium and find out the area under this curve. That gives me area under the curve. But you know that the error is very large. So I take number of points on the curve so that I can fit a trapezium between every two successive points. And then I'm going to get, this is a multiple application of trapezoidal rule. And Simpson rule, take 3 points and draw a parabola over that. And you find out the area under the curve using this formula. Again, there is a lot of error here. And if I take one number of points, so I can fit a parabola between these two, the quadratic between these 3, and again these 3, like that. So you can get the area in a better way. So since 3/8 rule, it takes 4 points. Okay, so a cubic line. This is quadratic lines. So in that way, there are other methods. You need not bother much about it. Romberg integration and Gauss quadrature. Okay, so there are other methods like that. And again, there are trade-offs. And mainly, we are interested in what is the order of the error. Okay, so it depends on what is the interval, and h is the interval. So it is of the order of h cube. This is order of h power 5, Simpson's 1/3 rule. And the 3/8 rule is h power 5, like that. So the order of error, based on what is the order of error you need if you want a higher approximation, like that. Okay, and this solution of ordinary differential equations, how to go about it? People are there?
Yes, sir.
Yes, sir.
Okay. So here we know that, okay, this is an example. How to find out, why to find out the area under the curve. Okay, so W is equal to f cos theta integral. So I have to find out, because knowing f and theta, and I can find out what is f cos theta at different values of x, and the area under the curve will give me the work done. Okay, so these are some of the applications. And method of solving ODE, we have Euler's method and Ralston's second order, that is Runge-Kutta second order and fourth order methods. I have seen your syllabus, both are there. So these are the formulae, just to recollect. And what are the order of error? You see them, right? And I don't know whether you studied predictor character methods. Have you studied predictor character methods?
No, sir.
No, sir.
Yes. Okay. If you didn't study, just ignore them. Yeah, just go through whatever methods you have done. And other methods, you can just study if you are interested. Because we are going to study predictor character methods while solving partial differential equations, but not ODE. So, but you can have, that is predictor means you just assume some value and substitute them and get a corrected value and put the corrected value, and then you will get exact value like that. So there are two steps, predictor method step and corrector step for each. And again, there are trade-offs. And these are the applications. Suppose this is actually, we use all those methods to solve first order differential equation, Runge-Kutta method and all. If I want to solve second order differential equation, I have to split them into two first order equations. Okay, suppose I have this d square theta by dt square plus g by l sine theta equal to 0. G by L sine theta. Something like this. I have to divide this into two first order equations. I have to assume some d theta by dt is equal to some x. Okay. So then this will become dx by dt. So this is one first order equation and this is one first order equation. It will become simultaneous two first order equations which are to be solved. Okay, that is the way I have to go about it. You can see, I think, yeah, d dt by dt equal to v and dv by dt is equal to minus g by l sine theta. These two equations are to be solved, again using Runge-Kutta method. Okay, and okay, that's it. This is about PDE solvers. We don't need it. Okay, so this is where I will stop here. So just quickly, I will go through one small story. Okay, there are 2-3 stories I have here, but I will go to the small story. The warrior's destiny. A great Japanese warrior named Nobunaga was going to war with a fierce enemy with only 1/10 the number of men the opposition commanded. Okay, so he has very less strength. And he knew that he could win the fight with a well-planned strategy, but his soldiers were in doubt. And on the way, the leader stopped on a Shinto shrine, there is a temple, and told his men, after my visit to the shrine, the temple, I will toss a coin. If the head comes, we will win. If tails, we will lose. Destiny holds us in our hand, in her hand. Okay, the God will see it. And Nobunaga entered the shrine and offered his prayers. Then he came forth and tossed the coin in front of his men, and heads appeared. And the soldiers were filled with confidence because the goddess or will support them and were eager to win the battle. And then one of the soldiers told, no one can change the hand of destiny. One of his attendants told him after winning the battle. They won the battle, and one of the soldiers told, destiny is there, decided. And then he told, indeed not, said Nobunaga, and showed the coin, which was doubled with heads on both the sides. Actually, both sides heads is there, but because it came as heads, so people got confidence that they will win, and they won it. Okay, so it is that the only person you are destined to become is the person you decide to be. Okay. So thank you. Somebody is calling me continuously. Thank you very much. See you. See you all.
Okay, sir. Thank you.
Okay.
Thank you, sir. Thank you.
Thank you. Actually, I have class from 1:30, and so my family, they are worried whether I have time for lunch and all. Okay. I think you also have less time for lunch. I had taken 1.5 hours. Okay, sorry. Okay, thank you. See you.